Hey, welcome back. Today we're going to be talking about more about what is angular momentum and how do you solve for the angular momentum of a linear moving particle. So this is something that AP Physics C mechanics students need to know, and it's a tricky problem. It's a tricky way of thinking about things. And in the past we've talked about torque, for instance, as a cross product. So I'm going to use that as an example to talk about how angular momentum is also a cross product. So let's do that. One way we've talked about torque as a cross product in the past is you can just find the sine of the angle between the two vectors involved. That's what we mean with that big X, that cross product here, is that we want the vector that is perpendicular to the other vector, so to speak. So for this you could say it's r times the force times sine of theta is one way to think about how to do a calculation with this. Today we're working with angular momentum though, and so angular momentum, one way of thinking about that is r crossed with p, where p is our linear momentum. So you could say L is equal to r crossed with, or in this case we'll just say multiplied with, mv sine of theta. So the theta is the angle in between the two vectors. I might do more practice with this and show you more about this angle later, but for now I've demonstrated this with 3 different drawings here, and what I've done is gone ahead and just drawn an arbitrary axis of rotation right here. And the question that I want you to think about is, does a linear moving particle, like we have right here, this particle is moving, this is its v value right here, does this particle have angular momentum? And it's tempting to think that the answer is no initially, but it turns out that there is some constant angular momentum for a linear moving particle, and that's what we have here. So we have our arbitrary axis of rotation, and if we say, well, angular momentum is going to be, one way to calculate that is the radius times momentum, linear momentum in this case would be mv, right, times the sine of theta, because that's going to give us the cross product component that we're looking for. And so if you do that, it turns out that this turns out to be 1 meter, the way I have it set up here. Well, it also turns out if you do that with different angles, notice how the angle changes and the radius changes, so therefore the sine of that angle changes and the radius changes. If you put those two together, you actually turn out with the same r sine theta value. So in this case, this is also 1 meter. And you can continue to do this. It turns out that the same value always applies. You still get 1 meter over here for our answer depending on how we set it up. So this is, I think, counterintuitive for a lot of people. It's tricky for a lot of people, I think, when you're first thinking about this. It's a commonly missed problem. If you see a problem like this, it could even be asked in a MCQ format, like compare the angular momentum of this linear moving particle to an arbitrary dot chosen as the axis of rotation. The answer, if you have a few options to choose from, would be something like it's going to be some constant value as it goes through. So that's the big idea here. It's really that straightforward. There's not a lot more to say about that, other than to say that I've done lessons on an entire year of physics, as well as almost an entire year of AP Physics C mechanics. So if you have any questions or comments down below, please let me know. And I hope you all have a great day. Take care.